Meerkat, one of the world's most sensitive radio interferometers, and a key facility operated by the South African Radio Astronomy Observatory, achieved a remarkable milestone when it detected radio absorption features caused by hydroxyl radicals, specifically OH molecules, associated with the interstellar object 3I/Atlas. This achievement was reported by DJ Pisano and collaborators in a notice submitted to the Astronomer's Telegram. The detection is scientifically important because it represents the first confirmed radio observation of 3I/Atlas, offering valuable insight into the physical conditions surrounding this rare interstellar visitor. The detection itself occurred during an observing session on October 24, 2025, when the object was at a very small angular distance from the Sun, only 376 degrees, which corresponds to 7 times the Sun's apparent diameter as viewed from Earth. Observing such a faint and distant object at such close solar proximity is technically challenging due to radio interference and solar background, which makes Meerkat's successful detection even more impressive. During this observation, the array recorded the presence of OH absorption in 2 well-known spectral transitions occurring at 1.665 and 1.667 GHz. Both of these frequencies correspond to hyperfine transitions in the ground rotational state of the hydroxyl radical. The 2 lines showed absorption features at Doppler velocity shifts of -15, 59 plus or -0, 16 kilometers per second and -15, 65 plus or -0, 17 kilometers per second, respectively. The negative value indicates that the absorption is blue-shifted relative to the expected rest frequency, implying motion toward the observer when projected along the line of sight. The absorption lines also exhibited full-width at half maximum values of approximately 0.88 plus or -0, 37 kilometers per second and 1.26 plus or -0, 40 kilometers per second. These widths provide important clues about the internal motions and thermal distribution of the OH-bearing material surrounding the object. It is notable that previous attempts to detect these lines with Meerkat on September 20th and September 28th, 2025 failed to reveal any measurable absorption. The null detections suggest that either the geometry of illumination, the column density of OH, or the background flux conditions were insufficient during the earlier attempts. The successful October 24th detection, therefore, resulted from a fortunate combination of improved geometry and perhaps a more favorable excitation or illumination state. The timing also coincides with the period shortly after the object's solar conjunction as viewed from Earth. This conjunction occurred around October 21st, 2025, when 3I/Atlas passed nearly behind the Sun from Earth's perspective, traveling close to the orbital plane of our planet. As a result, the velocity vector of 3I/Atlas at that time was oriented almost perpendicular to the line of sight from Meerkat. This geometry is important because the Doppler shift observed in any spectral line depends on the component of the object's velocity along the line of sight. The relative speed of 3I/Atlas with respect to Earth was the vector sum of Earth's orbital speed, about 30 kilometers per second, and the object's own heliocentric velocity, approximately 68 kilometers per second, giving a combined relative speed of 98 kilometers per second. However, because the line of sight at the moment of observation was oriented at an angle of roughly 9.2 degrees relative to the object's true direction of motion, only a small fraction of this 98 kilometers per second contributed to the observed Doppler signal. Specifically, the blue shift of about -15.6 kilometers per second corresponds closely to the projection of the full relative velocity multiplied by the sine of 9.2 degrees. This geometric agreement reinforces the interpretation that the OH absorption originates from material commoving with 3I/Atlas rather than from unrelated intervening gas. Another key insight comes from the determination of the thermal conditions of the OH molecules. At the time of observation, 3I/Atlas was located at a distance roughly 1.38 astronomical units from the Sun. Because solar radiation flux decreases with the square of the distance, and because surface temperature adjusts such that radiative heating balances radiative cooling, the surface temperature of the object would scale approximately as the inverse square root of the solar distance. This results in an estimated surface temperature of around 230 K, which is sufficiently warm to allow sublimation of volatile species such as water ice. When water ice sublimates, it can liberate OH radicals through photodissociation. The thermal motion of these OH molecules can then broaden the absorption lines they produce. At a temperature near 230 K, the expected thermal broadening corresponds to a full width at half maximum of approximately 0.8 kilometers per second, an estimate that matches closely with the observed line widths. This correspondence supports the idea that the OH molecules detected by Meerkat originated from the sublimating surface layers of the interstellar body and were not merely part of the surrounding interplanetary medium. The theoretical understanding of line broadening, including both thermal and non-thermal contributions, is a standard topic in radiative processes, as taught in astrophysics courses dealing with spectroscopy and radiative transfer. The detection of OH absorption represents an extraordinary step in studying 3I/Atlas, especially given earlier encouragement to radio observatories to monitor the interstellar object for possible radio emission. 5 weeks prior to the detection, concerns and suggestions had been expressed about the potential connection between the arrival direction of 3I/Atlas and that of the famous WOW signal detected in 1977. The WOW signal, received at a frequency of 1,204,556 GHz, was recorded at the Ohio State University Radio Observatory and has remained an unresolved and intriguing event in the history of radio astronomy. The coincidence that 3I/Atlas approached from a direction within approximately 9 degrees of the WOW signal's origin led to speculation that radio observatories might detect microwave or centimeter wave emission from the object. Although no such emission has been reported so far, the detection of OH absorption still constitutes valuable observational evidence. It also demonstrates that radio facilities are indeed monitoring the object, as had been promised by teams operating instruments such as Meerkat. Meanwhile, the trajectory of 3I/Atlas through the solar system continues to give astronomers opportunities for follow-up observations. According to orbital predictions, the object is expected to pass within about 53 million kilometers of Jupiter on March 16, 2026. This close approach provides a unique and rare opportunity for in situ or near-field radio observations by spacecraft already operating in Jovian orbit. In particular, NASA's Juno spacecraft is equipped with a dipole antenna capable of detecting low-frequency electromagnetic emissions in the range of 50 Hz to 40 MHz. While these frequencies are far below those associated with the OH transitions observed by Meerkat, they cover a broad region of the electromagnetic spectrum where plasma interactions, coherent emissions, or other low-frequency phenomena might arise if 3I/Atlas possesses unusual electromagnetic properties or interacts with the Jovian magnetosphere in a distinctive way. Juno's ability to perform such observations during the flyby window will complement ground-based radio measurements and might help to reveal whether the interstellar object produces any detectable low-frequency signatures. The broader significance of detecting OH absorption from 3I/Atlas lies in its contribution to the emerging field of interstellar object astrophysics. Since the discovery of 1I/Oumuamua in 2017 and the detection of 2I/Borisov in 2019, astronomers have recognized that interstellar visitors are more common than previously believed. Each new interstellar object offers an opportunity to observe matter that formed around other stars and was later ejected into interstellar space. 3I/Atlas, being only the third such object identified entering our solar system, is a rare laboratory for studying composition, outgassing behavior, thermal properties, and dynamical evolution under solar heating. The presence of OH absorption is particularly informative because OH is a common photodissociation product of water, and the detection, therefore, suggests that water-bearing minerals or ices are present. Furthermore, by analyzing the relative intensities, widths, and Doppler shifts of the OH lines, researchers can infer column densities, excitation temperatures, kinematic distributions, and potentially the effects of solar radiation pressure or charge exchange interactions. It is also worth noting that line absorption studies against the solar radio background at small angular separations are relatively uncommon. Observing near solar targets requires careful calibration, robust data processing, and strategies to mitigate the influence of solar radio noise. The fact that Meerkat successfully extracted faint OH absorption signatures under such conditions demonstrates the array's sensitivity and the proficiency of its operators. Such observations could pave the way for future work involving other interstellar bodies, comets, or small solar system objects that pass close to the Sun's position on the sky. As more interstellar objects are discovered by the next generation of all-sky surveys, especially with the Rubin Observatory coming online, astronomers will likely rely increasingly on advanced radio facilities to characterize their composition and physical behavior.